We have seen that in the magic technique we reduced a set of approximate linear equations to a set of exact linear equations. These set of exact linear equations were called the normal equations, and we have also seen that the normal equations always have at least one solution. There is one little issue that we have sidestepped so far, namely this system may have more than one solution. In that case, we cannot get any unique solution for the unknown quantities. How do we deal with that is the topic of this lecture. This is called the problem of estimability. For certain cases, we cannot find the solutions uniquely. But even in these cases, there are certain functions of the unknowns that can be solved for uniquely. And a very important theorem in this respect is called the Gauss-Markov Theorem, and we are going to take a look into that. Estimability, Gauss-Markov Theorem, Part 1. We start with the definition. A linear function c prime beta of beta is unbiasedly estimable if there exists t equal to t1 comma dot 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 comma tn transpose such that expected value of t prime y is c prime beta. That is, there is a linear function of y whose expectation is c prime beta. This might look somewhat confusing in the beginning. Just remember that beta is the vector of parameters and c prime beta, that is c transpose times beta, gives you something which is linear in beta. And the vector t is written with a transpose at the end because all the vectors in linear models are considered to be column vectors. Since it is difficult to write column vectors on the screen, so we have written it as a row vector together with a transpose symbol. Here are some properties. 1. Expectation of any component of y is estimable. In fact, expectation of any linear function of y has to be estimable right from the definition. But here is the rigorous proof. To prove the result for the ith response, consider the n-dimensional vector where the ith component is 1 and all the other components are 0. In other words, you are using only yi. Then, by the definition of estimable function, t prime expected value of y is an estimable function of beta and is the ith element of the vector expected value of y. Second property. Any linear combination of estimable functions is again estimable. The proof is quite straightforward. We start with any two estimable functions of beta. Call them c1 prime beta and c2 prime beta. Now, this means that you can estimate them unbiasedly. What does that mean? That means there are linear functions of y whose expectation equals these parameters. Let these linear functions of y be t1 prime y and t2 prime y, where t1 and t2 are two n-dimensional vectors. These vectors are fixed and known such that expected value of t1 prime y equals c1 prime beta and expected value of t2 prime y is C2 prime beta. Now we form any arbitrary linear combination of these estimable functions, which means you multiply them with any two numbers and add them up. Let us take the constants a1 and a2, multiply the first one by a1 to get a1 c1 prime beta, multiply the first term by a1 to get a1 c1 prime beta plus a2 c2 prime beta. Now take all the expected value of y part common to get a1 t1 prime plus a2 t2 prime times expected value of y, which is obviously a linear combination of expected value of y. This proves property 2. Now a word of warning is in order here. Whenever you are reading formulas like this, be careful to distinguish between the numbers like a1 and a2 and the vectors like c1, c2 and beta. If you see a transpose symbol or the dash or the prime symbol, you immediately know that that must be a vector. But sometimes the vectors also appear without transposition, like in this case y and beta. So it is very important for you to remember which one is the vector and which one is just a number. The fourth property goes like this: C prime beta is estimable if and only if C prime equals C prime h, where h is x prime x G inverse x prime x. The proof is the following. The property 3 that we proved just now gave us a necessary and sufficient condition for estimability in terms of C transpose equals C transpose H. To prove this property, we can proceed in the following way. First, let us assume that C prime beta is estimable. We are going to show that C prime equal to C prime H. Then from property 3, we have C prime H equal to T transpose XH, because C transpose was T transpose X. Then from property 3, we have C transpose H equals T transpose XH, because then from property 3, we have C transpose H equals T transpose XH, which is equal to T transpose X times, inserting the expression for H, X transpose X G inverse X transpose X equal to T transpose X, because we know from the property of G inverses that complicated expression involving X boils down to just X. Now T transpose X equals C transpose. To show that the converse is also true, assume that C transpose H equals C transpose holds. Then C transpose equal to C transpose X transpose X G inverse X transpose X equal to T transpose X, where T transpose equals C transpose times X transpose X G inverse X transpose. Thus we get that C prime beta is estimable. Look at the proof once again carefully, because here we have used certain properties of G inverses that we will get from our second tutorial on linear algebra. The fourth property goes like this: C prime beta is estimable if and only if C prime equals C prime H, where H is x prime x G inverse x prime x. The proof is the following. The property 3 that we proved just now gave us a necessary and sufficient condition for estimability in terms of C transpose equals C transpose H. To prove this property, we can proceed in the following way. First, let us assume that C prime beta is estimable. We are going to show that C prime equal to C prime H. Then from property 3, we have C prime H equal to T transpose XH because C transpose was T transpose X. Then from property 3, we have C transpose H equals T transpose XH because then from property 3, we have C transpose H equals T transpose XH, which is equal to T transpose X times inserting the expression for H, X transpose X G inverse X transpose X equal to T transpose X, because we know from the property of G inverses that complicated expression involving X boils down to just X. Now T transpose X equals C transpose. To show that the converse is also true, assume that C transpose H equals C transpose holds. Then C transpose equal to C transpose X transpose X G inverse X transpose X equal to T transpose X, where T transpose equals C transpose times X transpose X G inverse X transpose. Thus we get that C prime beta is estimable. Look at the proof once again carefully, because here we have used certain properties of G inverses that we will get from our second tutorial on linear algebra. Property 5. Given an estimable function C transpose beta, the quantity C transpose beta naught is invariant to the least square solution beta naught. What does that mean? This means that if you take a different least square solution, then C transpose beta naught is not going to change. That is, if and only if C transpose beta is estimable, C transpose beta naught is the unique least squares estimator of C transpose beta. Proof. To prove this property, we must show that C transpose beta naught is invariant to the solution beta naught we obtain to the normal equations. We see that C transpose beta naught equals T transpose X beta naught. The naught has gone to the top, it should actually come down, equal to T transpose X X transpose X G inverse X transpose Y. This is invariant to the choice of G inverse X transpose X, and hence to the choice of beta naught. Again, we have used some property of G inverses that we learned from the second tutorial on linear algebra. Now, the next two properties are stated first without proof. X transpose X beta is estimable, and so are the linear functions of X transpose X beta. And property 7, there exists exactly R linear estimable functions of beta where R equal to rank of X. Now, this statement requires some further explanation. It is not true that there are only R linear estimable functions. What is true is that the dimension of the space equals R. So, these are linearly independent estimable functions, because remember, if you have one estimable function, multiplying that by 2 gives you another estimable function. Multiplying it by 3 gives you yet another. So, if there is one estimable function, there are infinitely many estimable functions. The point is, they are not all linearly independent. This property claims that there are linearly independent estimable functions of beta, where R is the rank of X. The 8th property says the least square estimate of C transpose beta is unique if and only if C transpose beta is estimable. The proof is simple. Suppose beta 1 naught and beta 2 naught are two solutions to X transpose X beta equal to X transpose Y, that is the normal equations, or to X times X transpose X G inverse X transpose X beta equal to X times X transpose X G inverse X transpose Y, or to X beta equal to Py. Well then, X beta naught 1 must be equal to Py and X beta naught 2 must also be equal to Py. Since Py is invariant of beta naught, now suppose C transpose equal to T transpose X, then C transpose beta 1 0 equal to T transpose X beta 1 0, which is T transpose Py equal to T transpose X beta 2 0 equal to C transpose beta 2 0 as required. Now let us take a look at a number of examples. Consider the linear model y equal to x beta plus epsilon, where x is 1 1 1 2 2 2 and beta equal to beta 1 beta 2. The question is beta 1 plus beta 2 estimable? Here C transpose is 1 1, since C transpose beta is beta 1 plus beta 2. The column space of X transpose is spanned by just one vector 1 2, because all the rows of X are the same 1 2. Hence we can see that C does not belong to column space of X transpose, and so beta 1 plus beta 2 is not estimable. How do I know whether some particular linear parametric function is estimable or not? There is a theorem for that. The theorem states, suppose lambda is a P cross R matrix of constants, then the R cross 1 vector of linear functions of lambda prime beta is estimable if and only if there exists an n cross R matrix of constants P such that P transpose X equal to lambda. Let us take an example. Again, consider the linear model y equal to x beta plus epsilon, where x is as before, first column all 1s, second column all 2s, and beta is again as before, beta 1 beta 2. The question is beta 1 plus 2 beta 2, beta 1 plus beta 2 and beta 2 estimable? So we are thinking of a parametric vector. In this case, lambda transpose beta is beta 1 plus 2 beta 2, beta 1 plus beta 2 and beta 2. So lambda must be 1 2 1 1 0 1. Further, lambda 1 transpose equals 1 2, which is in column space of X transpose. Lambda 2 prime, however, is 1 1, which is actually in column space of X transpose, and lambda 3 is 0 1 in column space of X transpose. Therefore, lambda transpose X is not estimable. Results: there exist exactly are linearly independent estimable functions of beta, where R equal to rank of X. Proof: by property 3 of estimable functions, C prime beta is estimable if C transpose equal to T transpose X for some vector T. Let T be an n by n matrix of rank n, and let C transpose be equal to T transpose X, so that C transpose beta denotes n estimable functions. Now for rank C equal to R, there are exactly R linearly independent rows in R prime, which implies that exactly R of the n estimable functions are linearly independent. Consider the model y equal to x beta plus epsilon, where we have the following matrix equation. The y consists of y11, y12 up to y31. The design matrix X has first column consisting of all ones, second column 1 1 1 followed by 0 0 0. The third column is as shown, 3 zeros, 2 ones and 1 0. Fourth column are all zeros except the last one, which is equal to 1. The beta vector equals mu tau 1, tau 2, tau 3, and the epsilon vector is given by epsilon 1 1 to epsilon 3 1. Since expected value of yij equals mu plus tau I for j equal to 1 to ni, I from 1 to 3, we have expectation of y1j minus y2k equal to mu plus tau 1 minus mu minus tau 2 equal to tau 1 minus tau 2 equal to zeta 1 plus zeta 3 equal to 0 1 minus 1 0 beta. So that there exists a vector t equal to 1 0 0 minus 1 0 0 such that T transpose expected value of y equals tau 1 minus tau 2, which implies that tau 1 minus tau 2 is an estimable function of beta. Similarly, since expectation of T transpose y equal to mu plus tau 1 for T equal to 1 0 0 0 0 0 0, we see that mu plus tau 1 is an estimable function. To generalize, if you have mu plus tau I or something even more complicated like I equal to 1 to 3 and tau I minus tau k, I not equal to k, I k equal to 1 to 3 are all estimable, as are all linear combinations of such functions. In this model, rank of x is obviously 3, so that one set of linearly independent estimable functions consists of tau 1 minus tau 2, tau 1 minus tau 3, tau 2 minus tau 3. In this module, we talked about the linear algebraic underpinning of the methods used in linear models. We saw the problems of estimability and how we can solve them partially. But we are not yet finished. The next module will continue the same theory further.